Hello everyone and welcome to a new video. Um, Today we will discuss three-body interactions, three-body potentials, and in particular with relevance to covalent materials. So the topic today is potential for covalent bonding. Well, there is no um, there is no way we can get rid of two-body interactions, so they will always be there. But there is an extra component that could be present, which is the three-body component. So let's actually write this here briefly. There is usually two-body, but the new thing which we didn't cover before, whether for ionic materials or pure van der Waals interaction, is that there is a three-body component as well. Now let's take things step by step. Suppose I have molecular species that are covalently bonded, but in the molecule there are no two bodies. So sorry, no three bodies, only two. So for example, let's take simple gases like the hydrogen gas, the oxygen gas, or any of these dimolecular gases. So in such cases, so we are discussing here dimolecular gases. There is a covalent bond, but there is no three body. What we have here is maybe two hydrogen atoms and another two hydrogen atoms. So what the simple physical picture here is that within each molecule, we have a covalent bond. There is a covalent bond here and there is a covalent bond here. But between two molecules, it's not a covalent bond, of course, but there is some sort of two-body interaction, and it's not Coulombic. So the only type of interaction you get between two atoms in different molecules is some sort of van der Waals-like, which is typically modeled using Lennard-Jones potential, which we covered in a previous video. So within the molecule, you have a covalent out between two molecules. Well, let's call it this the chemistry way, the intermolecular. There is a van der Waals interaction modeled by Lennard-Jones. So in summary here, intermolecular, we do have van der Waals, while intramolecular, let's write this in yellow here, intramolecular, there is the covalent bond. Now, Lennard-Jones has been covered before, but how do we represent the covalent bond between two species? The simplest model for this, it's a two-body potential, is just harmonic spring. Basically, I'm assuming that there is a harmonic spring connecting these two hydrogen atoms belonging to the same molecule. You can write it as half k r minus r naught square, where both r naught and k are fitting parameters. So these guys are fitting parameters. Of course, if one is unhappy about the harmonic potential, so this is a harmonic spring, right? There are actually available unharmonic interactions, but we will not go in depth into that. I mean, it's just here to give the flavor of possible types of interaction. You can, of course, there are more sophisticated functions to describe unharmonicity in covalently bonded materials, but simple harmonic spring is good enough. Now, do we have a three-body term here? No, because the smallest entity, the smallest molecular entity here has two bodies only. Now, if you have molecules with three body in one molecule, so now let's say like H2O, maybe CO2, maybe any molecule that have more than two atoms will contain, here we will have both two body and three body interaction. The purpose of the three body is to fix certain angle. So the goal here of these three body interactions is to maintain a certain angle. Remember, In our discussion of covalent bonding in a previous video, we said that one of the characteristics of the covalent bond is that there is certain fixed angle in space. For example, let's take the water molecule. So the water molecule is known to have hydrogen, oxygen, and another hydrogen, and this angle is characteristic for the water molecule. It's 104.5 degree. Take the CO2 molecule. Again, we do have the carbon atom, and then oxygen, and then another oxygen. There is a characteristic angle here, which is 180 degrees. So let's continue discussion in another page. Let's take two water molecules, for example. Let's take another page. So suppose we are discussing two water molecules. So I have here an oxygen and another oxygen, and maybe here is hydrogen, and a hydrogen here and a hydrogen here. Okay, so let's see. Within one molecule, there is a covalent bonding between oxygen and hydrogen. There is a covalent bonding between oxygen and hydrogen. But in addition, you need a three-body term. Let's draw this way. Three-body term to maintain a 104 degrees angle. So you need a three-body term, which is still representing the covalent bond. Now, the OH bond can be represented within one molecule. So remember, this is intra. Within one molecule can be simply written as the previous harmonic expression, half K R minus R naught square. And again, the K and the R naught are fitting parameters. Let me make sure that I wrote square in the previous page. Did I? Yes, I did. Okay, very good. So that's the intra-OH bond. Additionally, you need to maintain the HOH angle. And again, this is intra-interaction. Well, the simplest thing is a harmonic angle, similar to the harmonic spring. In fact, with complete analogy, it's going to be V of theta. It depends on the angle theta, and it is half K, but it's another K. It's a different K. So, for example, I can call this K1, and this is maybe K2, theta minus theta naught square. In fact, K1 has different units in comparison to K2 as well. So if you look at units, this is energy, electron volt. This is a square of a distance, so it's angstrom square. Then the K1 here will have units of what? Electron volt per angstrom square. Meanwhile, here this is in radians, or you can call it unitless, so it's radians square, which is nothing. Radian is not a unit really. This is electron volt, and that actually makes K2 here in units of electron volt per radian square. So you have these fitting parameters theta naught and K2, which the developer of the potential need to develop. Again, this is a three-body term. So this angle here is a three-body term. Does that deny the existence of Lennard-Jones or van der Waals? No, definitely, but it's between molecules. So, for example, there could be hydrogen-hydrogen interaction, although that's rarely present in water models, but you could have it. It does exist, but very rarely. So there could be hydrogen-hydrogen, so there could be HH intermolecular, and typically this is a Lennard-Jones. There could be definitely oxygen, and again this is van der Waals and it's a Lennard-Jones, so oxygen. It's intermolecular, it's Lennard-Jones typically, could be other function. And then in addition, you also have the oxygen-hydrogen, which is sort of hinting to the hydrogen bond. And as such, you would have oxygen-hydrogen. It's intermolecular. Typically, it's modeled also as a Lennard-Jones. Although, strictly speaking, that's taken care of in an implicit way of the hydrogen bond, which is not pure van der Waals, or it's the hydrogen bond has its own nature. But most of the developers of water potentials, they decided just to use these set of van der Waals to implicitly account for the hydrogen bond, in addition to something else, which is Coulomb. So there is electrostatics in water, you know, and covalent material could have some partial ionic character. So there is electrostatics, and this is intermolecular interaction. And the way it goes is that typically hydrogen is associated with some small positive charge, not formal plus one, because then it will be pure ionic, but it is something like plus zero point 0.4 typically, and oxygen is negative zero point 0.8. Remember, there is more hydrogen than oxygen, hence the ratio in the charge is half. So water is one example of a material where you find covalent two body, covalent three body. You find van der Waals intermolecular, and you find some electrostatics as well. So it has both a covalent, an ionic, and van der Waals interaction. Same analysis go to any uh, three atom molecules, or molecules made out of three atoms or more, except that depending on the character of the molecule, there might not be columns. So maybe the molecule is really doesn't exhibit any ionic character, so you don't see any column interaction. Now, covalent bonding in crystals. So if you look at what we discussed so far, we discussed how do you represent the covalent bond in dimolecular species, diatomic species. Sorry, why I'm saying it dimolecular? That's actually not good. These are diatomic uh, molecular gases. Yeah, apologize for this. In triatomic molecular gases as well. We also discussed this. But now how does this look in crystals? So let's open another page. So two body and three body in crystals or solid state crystals. Okay, crystals. Again, if you have covalent bond between three atoms or among three atoms connected together, maintaining certain characteristic angle in space, then you need the three-body term. So let's take the classical example is silicon. So silicon is the classic example for this. And in silicon crystals, of course, it's hard to draw this in three dimensions by hand, but typically you have every three atoms um, making a characteristic angle of 19 degrees. So here now in silicon, you do have the standard Lennard-Jones between each two silicon atoms. And I cannot talk about inter and intramolecular because this is not really a molecule. It is actually a crystal. So there is usually a silicon-silicon interaction, which is two-body, which is Lennard-Jones or Lennard-Jones-like. It doesn't have to be Lennard-Jones explicitly. And then you could have something that connect these two silicon atoms by springs if you need. It really, silicon is a little bit, special. So it depends on the kind of potential that you are studying. But the most important is to maintain the 109-degree angle, the tetrahedral angle. And this really needs a three-body term. So this is three-body. And really you can have anything. Theta minus theta naught all squared, like in the previous slides. In one of the famous potentials that exist in literature is called Stellinger-Weber, what you have is actually something like cosine theta plus 3 plus 1 over 3 all squared. So there is some term that represents the angle theta. And depending on the value of theta, you get your energy. Of course, there are other terms here which I am not writing, and I refer the interested reader to the classic Stellinger Weber potential. This I think developed in 1985. If you are interested, but the key idea is that you have to have something to represent the angle. As I said, you could have also something to represent some sort of bond between silicon and silicon. It's up to you or the developer of the potential. The thing is, you need to succeed in reproducing properties of silicon and its different phases, including maybe liquid silicon. Okay, I have to point out something, a subtle point here, which I hope is intuitive. When we discussed water, uh, there's an angle here, but the angle is centered on oxygen. So you have HOH. So for every water molecule, there is one angle. But let's go to silicon crystal. Here, there is no clear center. So you could have this as a center, and then these are the arms, right? Or you might actually have another silicon atom here, where now this is the center, okay? This is a center, and this is an arm, and this is an arm. So there is another angle here, 109. So each silicon atom is entitled to be both a center and part of the arms of the angle, okay? And that actually makes the number of three-body interactions in silicon crystals is large, because, as I said, each atom is entitled to be both as a center and a periphery or an arm for an angle. Okay. All right. Let's summarize what we discussed here. In practical videos which we'll present later, we will show examples of these potentials. So let's summarize. Potential for covalent materials. Typically for covalent materials, especially if you have um, more than two atoms per entity, the entity could be a molecule or a crystal, right? If you have more than two atoms, then you have a two-body term and three-body term. If you only have two-body entities like diatomic molecules, like the hydrogen molecule, so there is only something that represents the covalent bond inside each molecule, but there is no three-body term, right? And the simplest of which is the harmonic potential we discussed here. Now, if you have triatomic molecules, then, well, sure, you still have two-body interactions, but the new thing are the three-body. And the purpose of the three-body mainly is to maintain these characteristic angles in a space. We discussed in details this in water. So water is a very important model system where you have covalent bonding intra both two-body and three-body. You have a lot of van der Waals and Lennard-Jones, and you do also have some electrostatics as well between molecules. So it's actually inter. It's very rare, as far as I recall, it's very, very rare to have electrostatics within the same molecule, which is intra. Again, this is up to the developer of the potential, but I'm telling you the common trend in literature, if you wish, is just for intermolecular interactions only are the ones that have electrostatics in water. And finally, in crystals, well, in crystals, these are extended systems, so you definitely have the two-body and three-body. And the classic example here in silicon to maintain the tetrahedral angle. One thing to be cautious about in crystals is that each atom is supposed to be a center and a periphery of an angle, an arm of an angle. Well, thank you so much, and see you in the next video where we will discuss interactions for many body interactions for metals. Thank you.